Welcome to the first online question and answer session. It went okay. There's one part in the middle where I stopped recording and I should have been recording, so you'll see some code just appear, and then I try to explain it when I realized that I wasn't recording. Sorry about that. I think I'll get better over time, but hopefully it's useful anyway. So, any questions? Okay, so the question is, what's the relationship between grades in this course and declaring the LNSCS major? The details will be posted just as soon as I get somebody to proofread them, but the gist of the policy that's about to be released is that there won't be any negative consequence to keeping your PNP default grading scheme, which the university imposes. The way we make sure that there's nothing bad about that is that you can choose to exclude the grade that you get this semester in 61A from your declaration GPA, as long as you take 61B at some point. So basically this course's grade could not count at all if that's what you choose to do. You can include it if you get a letter grade. You can also get a P in this course and request from me what your letter grade would have been. And I will compute it for you. And then you can choose whether to exclude or include that grade in your declaration GPA. So basically, if you do great, you can get a P. And if you would have gotten an A, then you'll include in your declaration GPA that A. If you get a P and you would have gotten a B minus, you can choose to exclude that grade. So the goal of this policy is twofold. One, you could just keep PNP and there's no downside with respect to declaring or for major requirements when it comes time to graduate. And the second part is if you do great in this course, then that can count toward declaring. And if you need to not do great because there's a lot going on in your life, that won't count against you. So here's another question, which is, what's the role of helper functions in Scheme and how do they work and are they different than Python? The answer is that the semantics is extremely similar. So let me show you an example. Should be the case that you can see window here. It's just a text file. If I define f of xy, which returns x plus y, well, there's no helper function at all. But if I define f of x, which defines g of y, and that returns x plus y. Well, what is it that f returns? How about g? This is like the make-adder function that we had before. So any function that's defined, or I guess in Scheme they're called procedures, any procedure that's defined within another procedure can reference in its body names for that local procedure, but also names for the non-local procedure. In Scheme, they're not called names, they're called symbols, because you can have stuff like plus in addition to x and y. And yeah, there's really no difference. So you don't need to like learn how to use helper functions in a new way. They behave in just the same way as they would in Python. If we instead defined this outside, like up here, then we'd have a problem. And the problem would be that whenever you call g, it won't know what x is. So you could still call f and get g back, and you can still call g, but then you'd get an error that says x is undefined. So the advantage of putting it inside is that you can refer to this x inside the body of g. The second question was, when will the policy that I described be formalized and released? I have been attempting to formalize it all day, And now it is in the proofreading stage where I make sure that all the other faculty that were involved in making that policy agree that I wrote it down correctly. And then it will be released. We don't want to release it with bugs. We want to release it in a way that makes sense to everybody and can be understood. And since there's like a little bit of nuance about all the different things that could happen during spring 2020 and in the future, students in 61A and 61B at the same time and all kinds of crazy stuff like that, it's just taking a little while to get all the details written down, make sure we covered all of our edge cases. So we're doing our best to get it released today or tomorrow, but I need some people to proofread it before I can post it. Okay, and another question is, what about the final in this course? Man, that is a great question. All the faculty right now are discussing what to do about final exams. My best guess is that it will resemble to a large degree final exams from previous semesters. As opposed to the midterm 2 was kind of quite different from previous semesters because it involved writing programs and testing them along the way. Which was, an exciting experiment for me, but didn't go so smoothly. So I don't think that we're going to try to do that again for the final. Instead, I think the final exam will look like a typical paper final. Now, exactly how it's administered, whether it's on a physical sheet of paper or whether it's on B courses or something like that, I haven't figured that out yet. But as soon as I know, I'll tell you. But I don't know yet because we're going to run some experiments, figure out what works well, and make sure that it's not, that it doesn't use quite as much technology as the midterm so that fewer things can break. And follow-up question is, on the final, can you use an interpreter in your computers? That is to be determined. I'm going to go through one example that someone asked about on Piazza because it seemed like a good question. And then I'll come back here and check if there are any other questions, and then we'll call it quits. Okay, so I'm going to share this again. Hopefully you can see that. As one of the lecture examples, I defined how to take a square root. Maybe I'll do an interactive thing first. Hold on. Where's my terminal? There it is. Okay, so we'll start up Scheme. And let's say we want to take the square root of 256. Well, if x is 256, then I want to guess what the square root is. Now, how do you know whether something is the square root? Well, you could square it and see what you get. So is 12 the square root? Well, I square 12, and I didn't get 256. Okay, so 12 must not be the square root. But it turns out that you can get closer to the square root based on an existing guess. If I guess that the square root is 12, and then I square the guess, I know that I'm wrong because I didn't get 256, but I could get a better guess with this trick, the Babylonian method, which involves averaging average of x and y is x plus y divided by 2. The way you get a better guess is take an average of your current guess and x, the thing you're trying to take the square root of, divided by your current guess. 16.6. What is this number? This number is supposed to be a new guess about what the square root of 256 is. Really what I should do is say, this is my new guess. And is it the square root of 256? No, it's the square root of 277. So I need a new guess. What is my new guess? 16.01. Is that the square root of 256? Almost. It's the square root of 256.4. What if we do this trick a couple more times and then see what our guess is? Now our guess is basically 16, which in fact is the square root of 256 with, a little bit of numerical precision that's wrong because we only did this procedure 1, 2, 3, 4 times with some arbitrary guess that wasn't very good at the beginning, 12. So maybe I'll just paste in the code from lecture. Looked like that. This says if you want the square root of x, then you need a way of improving a current guess, which might be 12, and this is going to give you back 16.66. But we don't want to just do it once, we want to do it many times. So that's what this procedure does, is it takes in some initial guess of 12. If the square of 12 is 256, which it's not, then we'd be done. Otherwise, we'll improve that guess and then call square root iter on the result, which calls this again on 16.6, which would call this again, which would call this again on 16.01. And eventually, if we called it enough times, we'd actually get the number 16, which is the square root of 256. So that's how that example works. Here, this is basically Scheme's closest variant of a while loop. This is a recursive function that says while the square of x is not equal, the square of guess is not equal to x, call improve on it and assign that to guess. Now, instead of an assignment statement, we're just calling square root iter again, but calling square root iter assigns guess to improve guess. Yeah, good question. So what is this number 1? I just picked an arbitrary place to start. This is my first guess. So if I had applied this formula with x as 256 to a starting value of 1, what would have happened? I would have gotten 128, which isn't very good. But then when I do it again, I get 65, which is better. And then I do it again, I get 35. I do it again, I get 20. I do it again, I get 16. I do it again, I get 16.01. Do it again, I get 16.000. Okay, this is looking pretty good. And then you do it a few more times, and you just get 16. So this is a property of this method, that you can start out in a really wrong place, and you'll end up in a really wrong place. And you kind of maybe get closer, you sort of bounce around for a while. But once you get quite close, then you converge to the truth very rapidly. That's a characteristic of this method. So kind of guesses and checks for a while, but when it gets in the right range, then it converges quickly to the actual square root. Probably should have recorded all this con stuff. Maybe I'll do it later. Actually, maybe I'll recap for the recording. Somebody asked, what's the difference between if and cond? And I came up with these two examples, which are equivalent. If always chooses between 2 options, whereas cond can choose between 3 options. Okay, that was a recap for the video. Okay, so now someone asked, what about recursion? Depends. So maybe we'll do a simple one, like
Fibonacci.
Fibonacci. Define fib n. It's typical that you'll have base case, recursive case, and you can do those with cond or with if. So maybe we'll do it both ways. The way you do it with if is you'd say something like, if n is less than 2, so if it's 1 or it's 0, then Fibonacci number n is just n. So if it's 0, it's 0. If it's 1, it's 1. Otherwise, you don't have to write the word else. It's just the nature of if expressions that they have an else case right here. Otherwise, I want to add together fib n minus 2 and fib n minus 1. If one huge line is hard to read, then you're like a normal person. The normal way you'd format this is you'd say if has 3 parts, and so you could put them all on separate lines in order to keep yourself sane. You could say that there's the predicate that you're checking for the base case, there's the actual base case, and then there's the recursive case, which is this sum. If you wanted to achieve the same thing with a cond, it would look like cond. Then you can start writing down cases. If n equals 0, 0. Oh, whatever. But this needs to be in parentheses. So that's how you write one of the cases. If n equals 1, then 1. Else, let me just write this. Now someone asked about 3 different built-in procedures called equal question mark, EQ question mark, and the equal sign, and how they're different. And I didn't know, so I started messing around in the interpreter to figure it out. And here's the result. Sorry, I forgot to repeat the student's question. Okay, so let's check A, B, where we write down whether they're equal, and then whether they're equal, and whether they're equal. So 1 and 1. Oh, what did I do? Only print one thing? How annoying. Every semester I have to remember how scheme works.
I think you can use begin.
True. No, I don't think that's the issue. I think that we need to print a list of
I see.
Okay. This and this. Close the list, close the print. Sorry to make you watch me fumble around. I guess that's part of learning or something. And okay, so now if we check 1 and 1, they're equal, and they're equal. I believe that this is about number equivalency. Well, I was wrong. Okay, well, I know one place in which they may diverge is if I compare two structured objects. Oh yeah. Okay, so equal won't accept arguments that aren't numbers. Equal will recursively check whether the contents of some list are the same. And equal, I think, is like is. It will only check that it's really the same list or the same object. Okay, that's all for today. But in subsequent discussions with students, I did agree that I would do some review problems on Wednesday around environment diagrams. So I'll answer questions about the lecture, and then I'll do some review problems.